Thank you for inviting me. And when I agreed to give this talk, I was very happy that I don't need to talk to you about quantum, which I know nothing about. But then if I look at the title of this talk, I immediately have a problem, because if you want to spend and you want to explain Bloch equations in the context of MR, and then physical basic mechanisms of tissue contrast, then probably we should spend at least 2 sessions. I would bore you to death with it, so I decided to make some shortcuts, and I will talk to you about some practical issues related to relaxation and relaxation measurements in tissues, and if needed, I will mention Bloch equations. I have no conflicts of interest. So the Bloch equations, or Maxwell equation, as it's shown over here, it's just a simple classical description of magnetization of behavior of the spin, or the magnetization, which is a population of the spins, in the external magnetic field. And it just simply is a very simple equations that describes the rotation of this magnetization vector around the magnetic field. So in the context of a steady state, or the context of equilibrium, in which you put patients into the magnet, all the spins are processing, that's what happens. Now, you heard a lot about quantum in the morning. And quantum approach and quantum physics approach, this is what physicists should be doing, because really it tells you everything that you should know about the physical phenomena of NMR, relaxation processes, etc. The major problem once we go from sort of chemistry or physics or very basic NMR, and we enter the field of medicine, is the fact that nothing, or almost virtually very little, that we do in a very heterogeneous systems like tissues could be explained by quantum. So that's one problem. Another problem is just if you meet with radiologists or clinicians, try to explain to them quantum mechanics. They will be bored after 5 minutes. We tend to have intuitive sense of relaxation mechanism of tissue, and quite often we jump from from quantum description to classical description once it fits us. So, for example, and this is what happens when we talk about T1 relaxation, we have this kind of very nice picture that we derive from quantum. When you talk about T2 relaxation, we rather use classical terms. Now, if we look at these Bloch equations, we wouldn't have a job if it was the only thing that happens with the magnetization in the magnet and in the system. The interesting stuff happens when you actually start manipulating those spins, and then you enter the processes of T1 relaxation and other processes of exchange, etc., and diffusion, and etc. So probably all of you know that T1 relaxation is just simply a process of coming back to the equilibrium, and T2 relaxation is nothing else by simply dephasing. There are 2 different processes, one going on in the transverse magnetic plane, another one is going in a direction along the B1 axis. Quite often in an imaging context, we keep forgetting that T1 and T2 relaxation processes also occur during RF excitations, especially if this RF excitation is very, very long. And in the morning, we heard a lot about this fact and using actually what happens during the RF to manipulate the contrast. I will come back to this plot later on, but we were about to formulate the general equations of what happens with the magnetization in the external magnetic field and with the presence or RF field. It's a relatively very simple differential equation, 3 by 3, with a very easy solutions, couple of exponents. The only thing that we need to add the relaxation terms, 1 over T1 or R2, into the system, and also T1 relaxation as well over here. Now, that explains, and that equation is great if we want, for example, to optimize our sequence or try to find out what will happen with the magnetization once we must start manipulating it or once we start measuring this magnetization as well. Later on in the talk, however, I will mention that this is just the beginning. This kind of equation describes a very simple system which only has one spin pole relaxing with those two relaxation and processing and responding to RF pulse. And even if we do, so for example, in the case of T1 relaxation, the typical way that we measure T1 is inversion recovery, in which we use 180-degree pulse that inverts the spins to minus Z. We wait some time, inversion recovery T1, and in order to measure this magnetization, we tip it to the transverse plane, and we measure FID. And by varying Ti, we can basically map the T1 recovery. So in this particular case, Bloch equation is once again very, very simple. It is just given by this formula over here. And the solution to this equation, which is the general Bloch equation for T1 relaxations in the transverse plane, it's also very simple. It depends obviously on initial and final conditions. In this particular case, we start with -1 to 1. And that's also is a very simple solution to the problem. I present this curve in a sort of sigmoidal on the logarithmic scale, so exponential seen here looks like sigmoid. And the reason is, first of all, we typically do have logarithmic spacing of Ti to cover the wide range of T1 relaxation times. And the second, if we happen to have non-mono exponential T1 recovery, this curve stops being sigmoidal, and we see it quite nicely, much better than in exponential representation. This is the theory. The reality is, however, a little bit different, because we actually never are able to tip the entire magnetization to the -Z direction. 180 pulse is never perfect unless you are working in an NMR spectrometer with extremely short RF pulses. So in reality, we start with a magnetization that is slightly lower, which means that we didn't tip all the spins into the -M0, but a little bit of them. And therefore, that's the curve what we usually get. So first of all, if you fit this model into the data, you misfit it, and you don't have a very good fit, obviously. And the second, if you only use 2 or 3 points, you typically end up with T1 that is shorter, or apparent T1 that is shorter than the real one. Now, you can use inversion recovery, or you can modify this equation phenomenologically again, by simply taking into account the fact that magnetization doesn't start with -M0, putting this small parameter over here, which is basically a measure of how good your RF 180 is, and if A is equal to 1, that's perfect. If A is less than 0.7, you probably should come back and recalibrate your system because you really are dealing with a huge B1 inhomogeneities. Nevertheless, you can fit it with 2 parameters, or you can even use this sequence, although it takes a very, very long time to actually map B1 inhomogeneities. Obviously, almost no one nowadays is using inversion recovery to map T1 relaxation times in tissue. It takes forever to do it. You need to repeat this experiment many, many times over, and the TR is usually an order of seconds, so it takes forever to do it. We don't have time, we don't have patience. Axel Hase and many others came up with a slightly better scheme, which is called spoiled gradient echo, and depending on what kind of a vendor, that's called SPGR flash or FFE. And that simply is a tipping the magnetization a little, just by a small degree, having a small TR, and this is probably the equation that all of you might know as well, which also defines a sort of an Ertz angle. And this is a great sequence to have a T1 weighted imaging, but it also can and is used to map T1. You basically have T1 term over here, and this entire equation on this entire curve is a function of 3 parameters, TR, alpha, and T1. It's a nice thing to have. It's relatively easy to fit. Yet again, there is a problem, and the problem arises from the fact that you have B1 inhomogeneities, and therefore whatever you're prescribing as your RF excitation pulse, it is 5 or 7 degrees. It's usually not. You have some scaling factor. What it means is basically your definition of your x-axis is wrong, and therefore you end up with the curve like that. And yet again, you are simply using few of the data points to get the T1, and bingo, you usually end up with a T1 relaxation time shorter than it should be. And therefore you worry, or therefore in the process you have T1 relaxation that doesn't agree with the literature. That happens very, very often. Yet again, either you can map B1 field, or you can even use this sequence to test B1 inhomogeneities by simply looking at the zero crossing of it. There are many methods to assess B1, but I strongly would argue that if you are interested in quantitative measure of T1 relaxation, you really need to do B1 mapping first. So T2, coming back to T2 relaxation, so this is the spin dephasing that happens in X and Y plane. Again, the Bloch equation is relatively straightforward. It's a very simple equation to solve. The solution to this is exponential. Now, why therefore, and the standard way of doing this is obviously your spin echo experiment, in which you have 90 followed by 180 to refocus your magnetization, and then you vary your TE time if you are interested in getting the T2 relaxation. Physicists are doing something slightly different, and we do sometimes as well, to the variation of it, multi-echo, spin echo, or CPMG sequence, in which you repeat your 180 many, many times over, and in a single shot, by looking at the envelope of the spin echoes, you are measuring the sequence. Now, T2 relaxation has even greater problems than T1 has, in a sense that if you measure it and if you change the echo time, you would expect that it's, and by definition T2 is, independent on the echo time, etc., and it has a straight line. So it doesn't really matter how much you vary and what kind of echo times you are actually choosing, you should have the same T2. Reality is slightly different. Reality is that the longer your TE is, the shorter your measured T2 becomes, and if it's very, very long, you are actually reaching T2 star. And this is mostly the reason, again, why a lot of literature does not agree on the T2 values, and that we have this ongoing discussion, is the T2 field dependent or not. So why this is the case, that's one question. And another question is, can we actually use it for our advantage? So I hope that I'm not offending you by a very simple picture, what the echo time is, but we use it simply to get rid of B-naught field inhomogeneities related to the imperfect external magnetic field. So if you have spins in a different locations and basically and they are in a slightly in a gradient of magnetic field, so this actually varies with x, y, and z. T component is always there, but T component is actually related to T relaxation. Therefore, they are dephasing, and we need to do 180 to reverse them, their orientation, and they will meet again. The problem is that if during this echo time, those spins are moving in a different locations, they will actually experience a different field, different Larmor frequency, so their net phase will be different. And I am stealing the show from Dimitri a little bit, but I promise that's only the one slide that I will show. Basically, what I'm telling you now is that as far as it goes, spin echo is a great sequence to get rid of macroscopic B-naught inhomogeneities. But if we happen to have those field variations on the microscale of the cells and whatever, we are not able to shim it. And therefore, we are not able to refocus this magnetization. So this is what happens. This is a very standard picture of diffusion-weighted sequence. So we use this kind of a fact of in a diffusion weighting, we introduce the variation of the gradient, we call it diffusion gradient, just to tag those spins, and then we basically wait that they disappear from the picture. This is diffusion weighting. Used all the time very successfully. The issue is that if you do have a T2 relaxation measurement, you always locally you will have a small gradient of the magnetic field, microscopic one. And a very good example is blood. It has been shown by Tulborn in 1989 and then extended by Graham Wright in 2 years later. This is what happened with the T2 relaxation measured for a different echo time, 6 milliseconds, 12, 24, and 48. This is blood in which what has been varied is the level of the oxyhemoglobin. The oxyhemoglobin is paramagnetic, and therefore what you have a scenario with is to have your water that is inside the red blood cell, that if it is in deoxygenated blood, it actually feels the different, sees the different field than in plasma. The problem is that red blood cells are very permeable for water, and what happens is that particular spin will jump from plasma into RBC and vice versa, and won't be refocused. And since if you have a perfect 100 deoxyhemoglobin, no matter what your echo time spacing is, you always end up with about 250 milliseconds T2. But look what happens at the other point of the scales, which is around 30% of the exohemoglobin. If your echo time is relatively short, you have 100. If it's very, very long, it's about 20. So they are all over the place. That poses a problem, but it's also an advantage because you can actually use this to characterize this local field inhomogeneities. And in this particular case, Graham found a very nice formula linking the change in T2 relaxation and the level of the oxyhemoglobin. You can also, by the shape of the curve, look at what is the resident time of water inside the cell. So, coming back to sort of relaxation and the field strengths, this is another sort of misunderstanding in the field. We all know that, and we expect that T1 relaxation increases with the magnetic field simply because we increase the gap between the different energy states, and therefore it's difficult for a spin to come back to its initial position. It doesn't scale linearly in the sense that if you have a bunch of the tissues like liver, muscle, heart, kidney, cartilage, white matter, gray matter, and blood, all of them will have a T1 increase, but not necessarily by the same amount. And this is for some peculiar reason. Gray matter increases way, way more than, for example, cartilage does. And I will explain to you, or try to explain to you, why this is the case later on. T2 relaxation, from the very definition, should only depend on the local magnetic variations of the field that are dependent on time. But yet again, in the literature, over and over again, you hear the story that it actually is shorter at 7 or 9.4 Tesla. And it is. We measure that T2 is. This is the experimental fact. What I'm saying here is that we have to be very careful, both in terms of definition and in terms and the fact that if we do measure a T2 relaxation, we always measure it in the presence of the magnetic field in homogeneities, and therefore our final result probably will depend and will be T2 star or microscopic T2 star related. Nothing wrong with it, but I think in terms of comparing the data from one side to another, it is very important to quote all the experimental parameters. The other way of doing it slightly more robustly is just to minimize this background effect, which is just minimize your echo spacing, which cannot be done very easily. But if we have a 1 millisecond echo spacing, most of the tissues do not show this effect because you don't let those spins to escape from one side to another during 1 millisecond. Now, we used to tend, and we used to say very briefly, that T1 and T2 relaxations are a measure of how dense and solid the tissues are. And if it were only the case, then those two things should be correlated, and luckily for us, they are not. The correlation between T1 and T2 are relatively very poor for various tissues. That doesn't mean, however, that if you have a certain tissue pathologies, and quite often that actually happens, for example, in white matter, then in the process of demyelination, for example, those are correlated. But between the tissues, they are not. Also, they do not quite well correlate with spin density either. So it's a little bit more than the presence of the other macromolecules that are slowing the motion down that causes the T1 and T2 relaxation to change. It has to be yet another mechanism, and indeed it is. And the fact is that if we look at our regular tissue, we are dealing with a very heterogeneous system. We have spins inside the nuclei, mitochondria, cytoplasm, extracellular matrix, vascular, etc. Chemical environment of water in each of those compartments is very, very different. Diffusion is different, macromolecular content is different, motion is different. So therefore, all those tissue compartments should have different relaxation times. And if things were ideal, while measuring the properties, let's say T1 relaxation of the tissues, we should see all those components here. We don't. And we don't because water is in a constant movement. Water goes everywhere. Cell membranes, vascular walls are very, very permeable to water. So water jumps from intracellular to extracellular to plasma to RBC and back during the course of your experiment. Those times are actually, this process is actually quite often quite fast. that complicates the fact, but it's usually what we see in MR is just the average water molecule that spends some time in intracellular versus extracellular space. And only a few tissues in which this exchange process is slow enough that we can actually measure the effects of relaxation in compartments. We also have macromolecules, cell membranes, lipids, proteins inside the cells, DNA, etc. This is a pool of many, many proteins associated with these lipids and proteins. And those proteins also have an NMR signal. We don't measure them typically unless we are doing spectroscopy. But bear in mind that those proteins also exchange with water as well. And if they do change their T1 relaxation and T2, more T1 than T2, but they do. And because of that, we do see in most of the cases T1 relaxation being monoexponential, but we also do see those strange T1 relaxation depending on the tissue. But if we do have an exchange, that complicates the matter a little bit more, and this is one of the two mistakes that I made during the presentations and also in the syllabus. It should be Z over here. This is where Bloch equations comes very handy. So we do have these relaxation terms of one pole and another, but we add those two terms, allowing for the flux of the, and this is barotraum optics, of the protons from intracellular to extracellular and vice versa. And the exchange constant, which is the rate with which the magnetization exchanges with those two poles, it has a very intuitive explanation. It is just simply cell membrane permeability times surface to volume ratio. Which basically means that surface to volume ratio is the most important part of those two. If you have a very large cells, there is a little chance that your water molecule will escape it, so the exchange time is very slow, and vice versa, if the cell is very small, then it's most of the case. Inverse of it is even simpler to understand. It's just the average time that the water molecule spends inside the pool before jumping into another. This is another mistake that I make. It should be slow here, fast here. This is what we call the exchange regime. So if the residence time is much larger than your T1 or T2 relaxation for that matter, what happens is that your water molecule will stay in this field, and therefore you have a separation there. If you, however, have a fast exchange, which means that residence times is very, very short, before relaxing, the spin will go to the other pole. And consequently, what you would see is as follows. This is just a plot of T2 or T1 spectrum. It's just the populations of the spins that have the particular half-minute particular relaxation time. And if you don't have an exchange, ideal case, you would see those two components, intrinsic T1 or T2 relaxation times, and we would measure the spin density inside and outside cells. If it's a fast exchange, there is a total mix, and we see single component. This is mostly what we see in T1 relaxation. What we do see in most of the tissue is something in the middle. This peak starts to be larger, but also shifts. This starts to be smaller, shifts a little bit less. The major points that I want to make here is that a lot of people are using multi-component analysis to, for example, looking at T2 relaxation and different compartments, and this is what happened in white matter. If you do T2 relaxation, we have two very distinct components. And then you say, okay, that's the one guy that is for 24%. It's absent in myelin, so therefore let's call it myelin water, and I have a myelin water measure. But this is apparent T2 spectrum that only happens because you have also an exchange. If you don't have an exchange, this is how it would look like. So in summary, quantum works and works very well. If you do spectroscopy, that's what you should be doing. Double quantum coherence as well, and you really need to learn it. But bear in mind that it only works for simple systems. Once you go to the tissues, probably simple phenomenology will do the trick. And because of phenomenology, Bloch equations, one form and another, also they are phenomenological and they are very simple, are very helpful in complicated tissue environment. And last but not least, neither T1 and T2 are really constant. They are really dependent on how sloppy you are. Thank you very much.